אוקיי, בוקר טוב לכולם. אני אתחיל שנייה בעברית, רק כי ברוכים הבאים ליום הנודד השלישי והאחרון של השנה. Actually, this I can say in English. Welcome to the third day and last day of this academic year of the Quantum Center. עכשיו אני אגיד משהו בעברית. אני חייבת להגיד שזה תאריך קצת קשה לעשות בו את היום הנודד הזה. זה לא יכולתי לא להגיד, לציין לפחות את כמות הכאב והצער שכל כך הרבה אנשים חוו וחווים. אז אני רק רוצה לציין את זה, שזה לא נעלם לנו בתוך כל הדברים המאוד מעניינים וחשובים שאנחנו עושים. בסדר. אז אוקיי, אז היום השלישי הזה, sorry, now English. Okay, so the theme that is starting to be sort of clarified and constructed in this in these migrating days of the Quantum Center is the theme of choosing a topic. And basically that topic, seeing how choosing an interesting topic that is somehow related to physics, computer science, and math in interesting ways, and taking advantage of the collection of people here that come from all these three disciplines, and clarify and talking about this topic or the notion from different aspects and trying to see the connections, trying to get inspirations. So I think that the previous day was very successful in that sense. The topic was, just to remind you, it was quantum memory, and we had various people talking about, so Eli Cohen and Michael Ilan and Yuval Peled and Tal Barak. And they were talking about the different aspects of it, about quantum memory from the physics aspect, from the math aspect of non-uniqueness of Gibbs states, from the physics aspect of free energy, and from the computer science aspect of actually constructing a memory. And I think that, and from the connection, from the aspect of error correcting codes and local testability. And I think, to me at least, that was very, very clarifying, even just the idea of putting all these together. So the topic that we have chose for this day, I hope will have the same kind of ability to connect different things. And one of the interesting things is even just preparing it and trying to create these connections, it's already, for those who are preparing it, it's already challenging and interesting. And so the topic of today is notions of randomness and pseudorandomness, whatever that means, in quantum blah blah. Quantum blah blah, quantum states, quantum operations, quantum unitaries, quantum evolutions, quantum physics, whatever. And so what we'll see today, so obviously we're not going to cover even a bit of this vast topic. It's like it touches upon so many things. But we're actually going to concentrate on pseudorandom and random from using different definitions of quantum states and quantum and unitary matrices, and my hope is that by the end of the day we will have seen several ways to define it and to think about it, and the attempt and challenge to connect between them will lead to interesting things. So the first speaker is Zvika Brakerski, and he will be talking about this from the computer science and cryptography point of view, and he will be talking about pseudorandom. He will actually give a definition of pseudorandom states, unitaries. And basically where the usage in cryptography, maybe in cryptography, where basically the way this is used in cryptography, and maybe Zvika will say a little bit about it more, but essentially one can think of a situation in which things look random to somebody who doesn't have enough abilities, be it enough computational power or enough, or the window that somebody looks at the whole system is too small. It only looks locally at the state or the unitary, and so it looks random. And however, the information is global. So it enables hiding information in some sense, or encrypting information. I don't know if Zvika will maybe talk about some kind of application, but any application with that? No. Okay, but we'll see. But the idea of the implication of the ability to generate such matrices is kind of it's natural to come up with matrices and states that seem random to a weak entity but are not random. So just to put things in context, we're talking about random unitaries of n qubits. This means that we are talking about matrices on a 2 to the n dimensional Hilbert space, and that means that the vector space is 4 to the n or something like that, and that means that if you look at a box in a 4 to the n dimensional space, the number of points that you need in order to cover to get an epsilon net in this set. An epsilon net is a subset of points that sort of every point in the set is epsilon close to one point in the net.
Stay tuned.
Sorry?
Stay tuned.
Stay tuned to where? To you or to Ori?
I'm going to talk about it. So.
Okay, both. So this will be defined probably better later. But you want to cover it in some way. Notice that the number of these points, if epsilon is even a half, is doubly exponential. Doubly exponential means that even if if we're trying to get to all these matrices and we have only, say, polynomially many options at every point, polynomially many generators, we will not get there. We will not even get close there. We will only be able to get close to exponentially many, not doubly exponentially many. So we're very, very, very far from random unitaries in that sense. Okay, so we're looking at notions. So we are left sort of in a place where we have to look at matrices that mimic randomness but are not really random. Okay, so Zvika will talk about this and also about a connection to a very interesting problem called the unitary synthesis problem that he will talk about. Okay, so that's Zvika. Now, Shira, is Shira here already? No, but she will come, hopefully. So Shira from Beersheba, she will give us the physics point of view, more of the physics point of view, so in some sense, how is this related to physics? So in some sense, you can think of this notion of a random unitary working on some state as a scrambler, something that scrambles information. If you put something local, like an observable, on a single qubit, and you apply a random unitary, it will certainly not stay local. It will evolve or be mapped to something highly non-local. And this notion of scrambling is related to how operators spread in quantum evolutions. So spreading and scrambling. And this can be thought of as some kind of weaker conditions than actually being pseudo-random. It's kind of a signature that something random is happening, or a condition. And the connection between this notion of scrambling and operating spreading, as well as chaos that Jiro will be discussing quite deeply. This is to me very interesting to clarify what are exactly those connections. And just to say that she will actually point at a very interesting connection from what the motivation of a group of physicists studying this. There has been a very strong motivation over the past, 20 years even, I think, which is black holes and quantum gravity. So I wish you were here. She was here because she could have corrected me, but okay, the advantage is I can say anything. So she's going to talk about black holes, and black holes are thought of as the fastest scramblers. Sort of the fastest operations that in terms of creating this scrambling and randomness. So that's what she will be talking about. And how physicists look at these notions of randomness. Okay, so that's Sheila, and then comes Ori. Ori will be talking about another aspect of random unitaries, and that aspect is actually very much related to this notion of an epsilon net on the unitary group, and this aspect is basically it actually can be tied back to the Solovay-Kitaev theorem. How many people here have heard about the Solovay-Kitaev theorem? Okay, so the Solovay-Kitaev theorem basically says that if you have a set of generators that generates a dense subset of the unitary group, it does that very fast, exponentially fast. If we're talking about the unitary group acting on a small number of qubits, a constant number of qubits. So basically, a word in the unitary group written using L generators, a sequence of L generators G1 to GL. If you look at the best one, and you're trying to approximate a U in the unitary group acting on, say, 3 qubits, that thing in the operator norm will behave like something like log to some power over 1 over L. Correct me if I'm wrong, Ollie, but I think it's correct. So
this should be exponentially small.
No.
I'm sorry?
No, that way.
Yeah, L is logarithmic in 1 over epsilon. It's the opposite. It's a
I thought I would switch it and then that will fix it.
So it's e to the minus L to the 1 over C.
E to the minus.
Right, or something.
Let me put here simply log C of L. Sorry, log C of 1 over epsilon.
1 over epsilon. Then this is epsilon.
Okay, so if you want to get epsilon close, you need here a sequence of size log 1 over epsilon to the C. And I will talk, and how is this related to the pseudo-randomness? Well, basically, these words of length L start to span, start to get close to unitary matrices, and the question is how fast they do that, and how fast is related to this L, and how fast is not exactly the same as pseudo-random, because you can have sort of lumping, and then it will not look very uniform. But it's obvious that the two are tightly related. And Oren will talk about extensions of the Solovay-Kitaev theorem, this quick approaching to unitaries in the unitary group is obviously one of the most important theorems in quantum computer science, because a quantum circuit will then, if you write a quantum circuit in a particular set of gates, you can switch to a different set of gates using the Solovay-Kitaev theorem. So it basically says that it doesn't matter which set of gates you're using, and it gives us kind of a universality notion of what gates we're using. You can move from fault-tolerant gates to algorithmic gates, etc. You can move between the languages, and you only pay logarithmic factors. So I want to talk about the mathematical aspects of those. There have been quite a few interesting developments, and he will start from the basics and tell us this. And then we'll have Evgeny Belev, who is a physicist, and he will talk about, again, a different notion, but very tightly related to these notions of randomness, which is from the physics point of view, the eigenstate thermalization hypothesis. Eigenstate thermalization. I just realized that some people are probably not in the room because they're not in the Zoom. What about the Zoom?
Should work. He said. But
It should work? It's actually on?
well, we can ask the. I
There's
can
an icon of 3 people, maybe it's that.
Yeah.
Good, okay. So everybody in the Zoom, please feel free to interrupt also.
But maybe we should do like this. Ask one of them to say something that we can be sure that you're here.
You just did that, so. Can anybody on the Zoom say something?
Hello.
Hello? Good.
Yeah.
Okay. Hello. So the eigenstate thermalization hypothesis is a very interesting notion. It's a hypothesis. I think there's no real claim to even have it as a conjecture. It's basically a phenomena that occurs in many physical systems. I don't think it's really clarified when. Which states that eigenstates of large systems, when you look at small parts, if you look at a window of, say, a constant number of particles or, I don't know, a small number of particles, it looks like it's thermal, meaning it looks like the state is behaves like it is in the Gibbs state. And this is very weird because we're talking about a deterministic state. Why on earth would it behave randomly? And this notion of connecting between deterministic and randomness is something that is sort of tied between all these notions. And I think I've spoken enough, so I'll let Zvika talk. I'll just say that at the end we'll have I don't know, some discussion in which we will all attempt to provide insights on these connections. And I should also say that at the end, after this, that will be the end of the formal day, but then we'll have a student event in the same room, and that student event will include Alon Dogon, who will talk about, can you say the name?
Random unitaries and additivity violation of entropy.
Okay, and Itai will guide the students and whoever wants to stay in basically a guided exercise about a very important method that has been developed by Xandre called compressed oracles, and that method goes into what Zvika will say, at least implicitly, and it has become a very powerful method in cryptography, and it's very interesting, so Kai will do that, and there will also be pizza. Okay, Zvika.
Good. Okay, great. So let's start. Hi everyone. Can I walk around like audio persons?
Yes.
Is it okay if I walk around? Good. So as Dorit said, I'm a computer scientist, and this is going to be sort of my perspective on things. Wait, can I like these things? So this is going to be like computer science perspective on things. So I was trying to sort of be inclusive and explain what I mean as much as I can. But if I didn't, please ask. So I'm going to talk about joint work with Henry Ewan from Columbia, and this work sort of tries to relate notions that we're thinking about in cryptography. This notion called pseudorandom unitaries. And other notions in quantum computing, such as this problem known as the unitary synthesis problem. I'm going to say what it is, Basically, sort of, we're showing some connection between these objects, and in the course of this exploration, we're also sort of trying to discuss and relate notions that have to do, like different notions and definitions of pseudorandomness when it comes to unitary operators. So mostly we're going to talk about definitions. Hopefully, we're also going to get to our results, but we'll see about that. Okay. So, what are pseudorandom unitaries? So, this is a notion defined by G. Liu and Song. I want to get this out of the way. But, a notion defined by G. Liu and Song, and sort of the goal is to try to capture the evolution of a random quantum system. So, we have this unitary group over a d-dimensional unitary group. And the dimension is exponential in the number of qubits. So the number of qubits is going to be small n, and the dimension is going to be d. The dimension is exponential in like stuff, in the amount of resources that we have. So this is the way that we should think about it in general. So we can think about d as a parameter that is not necessarily related to the amount of computational resources, but as a rule, you should think about d as very big, okay? And we can define like this uniform distribution over unitaries. This is the Haar-random distribution. And I'm going to denote it by mu throughout this talk. So mu is the Haar-random distribution. And we want to sort of capture the idea that sometimes, a unitary gets sampled from the Haar-random distribution and gets applied to some states, okay? And, we want to be able to simulate or capture the behavior of this process. Okay, sure, just sample a random unitary, a d by d matrix unitary, and do whatever you need to do, but we want to do it efficiently. And as Dorit pointed out, and as I tried to sort of also argue just now, these unitaries are very big objects if you just try to represent them just in terms of information theory. So we need to think a little bit harder on how to get an efficient process that nevertheless simulates or captures the essence of this sort of inefficient process of sampling from the Haar-random unitary distribution. And I'm not going to say much about motivation, sorry Dorit, but like this thing where you sample from a Haar-random unitary and then apply it to stuff, I'm using like terminology that I'm not like that familiar with, so I'm hoping that this is correct. So this is used as a model for thermalization, black holes, and it's also useful in cryptography. So I think I covered like a bunch of the buzzwords here. So we're going to hear about thermalization, we're going to hear about black holes. So this is sort of a motivation for studying random unitaries. And so this is going to be like the goal that we have in mind. So what do we want? How do we sort of make this thing a little bit more explicit? So what we want a distribution of unitaries, right? So we have the Haar-random distribution. We're not going to get that. We're going to have some other distribution. And unlike the Haar-random distribution, this one needs to be like efficiently sampleable and computable. So I should be able to sample an element from my sort of distribution of unitaries, and once I sample, I have some like description of this unitary, I should be able to apply it efficiently to an input state. So this is the efficiency part of things. And we also, and the other part is we wanted to capture what happens for Haar-random distribution. So what we're asking for is for this for our efficient distribution to be indistinguishable from the Haar-random distribution. And I'm going to spend some time sort of explaining what we mean by indistinguishable from Haar-random. But again, intuitively, the point is that if someone sampled the Haar-random unitary and told us, tell me, and sort of gave us access to this unitary, we can give input and get output for as much as we want. We should not be able to tell whether we got a Haar-random unitary or a unitary that was sampled from our efficient distribution. And for the sake of establishing some intuition, and also because we're going to sort of need to apply it a little bit down the line, I want to tell you about sort of the analogous classical notion of pseudorandom functions. And you can see that this sort of goes back to the 80s. And the goal there was to capture the behavior of a random classical function. So again, we have functions that take n bits as input, and let's say output just 1 bit. So we're thinking about this distribution of random functions. And again, this is information theoretically, there's a lot of, like the description of such a random function is going to be long. It's going to be exponential. So we want to be able to do it efficiently. And so let's sort of see how we do it in terms of syntax. So again, we want to have an efficient algorithm. And this algorithm takes a key k, so the small k is a key, and given the key, you should be able to sort of compute this function f sub k efficiently. And also, like when we're putting forward this f sub k, it defines a distribution over functions. It's just a distribution f sub k where k is sampled uniformly from the space of keys, right? So this is a distribution of efficiently computable functions. And we want this efficiently computable distribution to be indistinguishable from an actual random function. And I keep using this word indistinguishable, and I want to say a little bit more what I mean by indistinguishable. And I'm going to start classically, and then we're going to talk about the quantum version. So I need to tell you what is this sort of class of distinguishers. So I need to tell you who is this experiment who's either getting a random function or like a pseudorandom function and is trying to tell them apart. So the first thing that we notice is that in order for things to make sense, this distinguisher only gets oracle access to the function. So it can't actually sort of see the description of the function because there's not that many f sub k's, right? So if I just show it the circuit that I'm using, it can say, oh, this is a circuit that looks like f sub k, and it's not a random. Like there's very few f sub k's and many actual functions. So if you see a circuit that actually computes one of these f of k's, then you know that you did not actually sample randomly, right? So I can't show you the circuit that I'm computing, but I can tell you, you can give me any input you want, and I'll give you the output. So this is what we call oracle access, right? There's an oracle, and you can give the inputs and get the output back.
You're assuming the distinguisher does know the family of FKs, right?
Right. Yeah. So because we constructed this thing, right? We are saying like we want to say there's a fixed family of pseudorandom functions, right? And yeah. So all of the uncertainty goes into choosing the key k, right? There's no uncertainty other than what is the key k that I chose.
I have a question. There's sort of a very big difference between random functions and random unitaries, obviously, because random function, when you get an input, you can, in principle, simply randomly choose an output, and then you only have to remember what you've done so far. So you can apply a random function, whereas a random unitary, it's much more difficult.
So let me say. So actually, what you're saying is not like about the distinction, I think, between random functions and random unitaries. It's about the distinction between classical access and quantum access to the function. So even if you're thinking about a classical function, but you get quantum oracle access, like you're able to query this classical function in superposition, you already have this problem that you mentioned. And and it's a problem, and it sort of is related to this compressed oracle thing that is going to be discussed down the line. But that's true. Like it's not so simple, like to do things. And what we want, all of our because we are in this quantum day, we're always going to think about our distinguishers as quantum entities, right? So even when we're talking about sampling a classical function, we still want to allow our distinguisher to query it in superposition. So I'm saying I'm giving you oracle access. You can still give me like a quantum state and tell me compute this function on this quantum state, and it should still be indistinguishable. So this is the game that we're playing. And I'm going to talk about two types of distinguishers. So oracle access is has to be the case. So the first type of distinguishers that we can think about is ones that only have a bounded number of queries. We said that we're giving oracle access, so I'm giving you input, you give me an output, you give me an input, you give me an output. How many times do you do it? If you have some bound on the number of queries, let's say you're doing it only t times, then there's a known information theoretic solution. You can use what's called a family of t-wise independent functions, and this is just going to give you sort of indistinguishability with respect to this class of distinguishers, so long as they're only making like a bounded number of queries. And the point is that in order to achieve this, the length of your key has to grow with the number of queries t, and it's not so hard to show this using just information theory, just the amount of information that you need in order for this distinguisher not to catch you that you're using a too small of a function family. So this was known I want to say for a very long time ago, but now I noticed that the gap between at least this definition and pseudorandom functions is not that, hasn't been that long before people thought about this other definition. Okay, good. So one type of solution, bounded number of queries, t-wise independent, key length grows with k. Now, the idea of GGM84 in defining the notion of pseudorandom functions is to say, okay, now I'm not going to bound the number of queries a priori, but rather I'm going to bound the complexity of the distinguisher. So now my distinguisher, all I know is that it runs in polynomial time, and it can make as many queries as it wants in the limits of this polynomial time. In the limit of this polynomial time. And sort of we want the key length to not grow with, so I'm saying I'm not, like, the number of queries that you can make is some arbitrary polynomial, but I don't want my key to grow with this arbitrary polynomial. I actually don't know the concrete running time of the distinguisher when I generate my function family. So I'm going to have like some fixed key length, and this key length is going to be sort of okay for even for very large sort of number of queries, so long as the adversary is computationally bounded. So we need to use like complexity theory and lower bounds and assumption and cryptographic assumptions. So this was sort of this beautiful work by Dorit Aharonov and Mikali, showing that you can actually do it from any one-way function, for those of you who care. But basically, what I care about is the definition. Yeah.
Do you mean here the polynomiality is that the complexity is polynomial in terms of the key length? Or?
Yes, it's polynomial in the key length, but I'm not telling you which polynomial, right? I'm telling you, okay, this is, yeah.
The input to the polynomial is the key length?
Let's say, yeah, sure. Yeah. So this is sort of the classical notion, and now let's, notions. Oh, sorry, yeah.
For the idiots. The second, the thing on the right seems to be in contradiction with the thing on the left. So can you explain why there is no such contradiction?
A contradiction in the sense that I told you that here the key length has to grow with t, and here I'm telling you that the key length can be much shorter. What is the contradiction?
Yes.
Okay, good. So here, like the adversary, it makes like a bounded number of queries, and then it can run an arbitrary computation, like an arbitrarily long computation on the results of these queries. Here, I'm allowing you to make maybe more queries, but you can only run like a polynomial-sized circuit on this, on the output of the queries. So you're actually sort of relying on the fact that there are hard problems in the world. There are things that you cannot do with like, small computational power, and you can do with large computational power.
But just to say, these are two different notions. They're not the same notion.
Yeah,
so on the left, you allow me arbitrary computational power.
Right, here I'm only bounding the number of queries. Beyond that, you can do whatever you want. Yeah, arbitrary computation. So it's Weizmann Carter. I don't know if that's this is the citation that I found. Like, it's one of these things where you like, you know that your paper made it very well, and people actually stop citing it and just say you can use TY's independent family. So I hope I got the right citation, but I'm not sure.
And on the right, it's a theorem, or it's a statement.
On the right, it's a theorem. This is like a theorem by Dorit Aharonov and Mikali. They showed actually how to do it, starting from like what we call the cryptographic assumption, like cryptographic building block. Basically, if you can do like any type of encryption, then you can also have this type of, you can also have this type of pseudorandomness.
Actually surprising.
Yeah, so we're doing, okay, yeah?
Can we have another question?
Sure, yeah.
So what Dorit suggested, the simulation, why don't we just use that, which is actually random, but you don't need to sample, it's like, why do we?
So this does, okay, so this thing, I don't want to like go into details but let me just say that this does not like satisfy this definition. In this like lazy, I don't want to, like, you don't need to sort of follow this answer. I want to, get Italian Dorit off my back, okay? So like here I want a fixed key length. In the lazy evaluation, you keep generating things, and like first of all you get a stateful solution, and like the length of your state is actually a priori unbounded. So here, like, we're not stateful in the sense that we're sampling the key once and for all, and it doesn't grow. So this is the difference.
But do we need it for something?
Yes, I mean, yeah. In some settings, you actually need this thing to not be stateful. Like everyone, I have many copies. Everyone can do it. Like I distribute it across many parties. Okay, so back to unitaries after we did like cryptography 101. So now we want to do the same thing for unitaries. So we want the distribution of unitaries. It's efficiently sampled and computable. indistinguishable from har via oracle access. And again, we have two choices of a distinguishing adversary. One is, again, computationally unbounded, so, but it only makes at most t queries to its oracle. And this is a notion known as unitary t designs. And similarly to before, you can get it with a key length that grows with the number of queries with information theoretic security. So it's computationally unbounded, except it can only make like a bounded number of queries to the unitary at hand.
Queries meaning apply the unitary on any state.
Right, yeah. It gives me like an input and I give it an output. How many times can you do it? T, at most T. So this is this notion of unitary T designs. And then this paper by Ji Liu and Song actually said, well, you know, we should really think about also the cryptographic notion. And again, hopefully after the previous slide, it's clear what we're trying to do here. Again, we're going to have a key. The size of the key is going to be fixed once and for all. And I'm allowing any quantum polynomial time adversary. It can make, again, polynomially many queries. I don't know exactly what this polynomial is, but the size of the key should not grow with the number of queries. And this is this notion of pseudorandom unitaries. And okay, I'm going to, let me just say, even though in the title of the talk it says pseudorandom unitaries, and also in the title of the slide, I'm actually going to care about both of these things. So don't forget about T designs. So we care about T designs and also pseudorandom unitaries, okay? Yeah.
Is it the same as a is it obtained by a random circuit?
There are, so you'd want it to happen, and I think there are some works that show that certain distributions of random circuits give you a T design. It's not immediate to show. That I mean, you want this random circuit is not going to be very big, right? It's only going its size is going to scale with like t and the number of qubits, but yeah, it's not. Yeah, so I think it is true for some distributions of random circuits, but it's not easy to show. At least, or to bound how deep the circuit needs to be and things like that.
When you say it's not easy, it was proved, but
it was proved, but recently, yes.
It was proved recently, and for specific distributions.
Right. It's not really. Yeah. What do we mean by random circuit? Right. Because we have 2-qubit gates. Do the gates need to be random? Yeah. So it's like random 2-qubit gates. Random. Like what do you have about the topology of your circuit? Is it also random topology, or maybe it's just like you know, shifting blocks or things like that. So all of these things, there are many people who are working on this thing. It's like a very rich area of research. I don't have like just off the top of my head like all of the sort of state-of-the-art results.
And when we say indistinguishable, does it involve some kind of a limit?
Right. So yeah, I was glossing over these things. I'm allowing a little bit of error, right? So like so in the end, like I'm allowing my distinguisher to interact in both of these notions. I'm allowing my distinguisher to interact with this like family of unitaries that are trying to be random. And in the end, it needs to tell me, is it random or is it pseudo-random? And it should not succeed with, and again, so it's not, I'm not requiring that it's going to be perfectly indistinguishable, but rather that like somehow the advantage that you have in distinguishing these things is small, exponentially small, let's say.
Exponentially in what?
In, let's say, the number of qubits. You can parameterize, so there's, as you can probably imagine, there are many ways to parameterize these things, but like, again, for like, the first intuitive thing that you have, the intuitive picture that you have in your head, think about exponential in the number of qubits. Okay, good. So let's again be explicit about the syntax here, just to sort of hopefully nail it down. So, like we had before in the setting of the random pseudorandom functions, we have a keyed family of unitaries. So there's this space of keys, and each key is associated with a unitary v sub k. And as I said before, there's like some induced distribution that I'm going to denote by nu. And this is just a distribution that is obtained by sampling a random key and giving you the unitary that's associated with this key, right? So I said I wanted an efficient distribution of unitaries that's indistinguishable from har. So har distribution is mu, and my efficient distribution is nu, and I'd want these things to be indistinguishable. Oh, and yeah, okay, I didn't say there's the efficiency thing, which is given the key, I should be able to efficiently apply this unitary v sub k on any input. And the pseudorandomness, so now this is like sort of a formal equation for what we said before. So we can think about this. A is an algorithm. It's an adversary. And we're going to say that like we have this like family of distinguishers. So this is what it means. Like A is coming from our family of distinguishers. And it gets oracle access to either a random unitary or to a unitary that's coming from our distribution nu. And it can do whatever it wants, and then it needs to tell me, do you think, if it thinks that it's har or not. So, and we model this just by outputting a bit. Let's say output 1 if you think you're har, output 0 if you think that you're like pseudorandom. And what we require is that sort of the probability that you're outputting 1 is going to be, so the goal of the distinguisher is to have like these two things be as far apart as it can, right? It wants to distinguish. And what we want is that this thing is smaller than delta, and delta is like some negligible function, so you can think about it as exponentially small, yeah, so for pseudorandom unitaries, A can be any efficient quantum polynomial time algorithm, and we want the delta to be negligible. And we can also think about this sort of t-design thing, where A is not necessarily efficient, but it's bounded in number of queries, and then delta is going to be like this approximation, like it's going to be what we call an approximate t-design, and we're allowing like some small slackness in the definition, if it helps us.
So, but in t-query, A is unbounded. A can be any.
A can be computationally unbounded, yes.
Information, it's information.
Information theoretic, yeah. Mm-hmm.
Can you explain or write the formula for what is AU, or what the algorithm does?
So it can do whatever it wants. So you can, so one way to, sorry?
What is do?
What is an algorithm? An algorithm can do whatever it wants, right? It's like, so you can think about it as we can think about it, just a second. You can think about it as a quantum circuit that also has like U gates or V gates, okay? Does this help? Yeah. Okay. So to me, this is synonymous to saying an algorithm that has U as oracle. So sorry for not.
Yeah, it's a quantum circuit that has some register on which you can apply U, and then it runs more gates on more qubits, again calls U, etc.
Yeah. Right, good. So this is, so these are the objects that we're going to talk about, now I'm going to introduce another one. Yeah, it's going to be something, I'm going to try to connect these things, right? So I told you about like t-designs and about pseudorandom unitaries, but sort of what we're, the starting point actually for this work is noticing that actually the way that we construct pseudorandom unitaries actually goes through a construction of t-designs with special and interesting properties. So this is what I'm going to explain. So what I'm going to describe is like the predominant framework for constructing pseudorandom unitaries, like this thing with computationally bounded, right? Remember pseudorandom unitaries versus t-designs. So I want to tell you how people actually go about constructing pseudorandom unitaries. So the first step is to sort of relax the problem. So remember I told you before that like what we want is a key of some fixed length. So instead of instantiating these unitaries using like fixed length keys, now we're actually instantiating them using functions, using long classical functions. So just think about functions that go from 0, 1 to the end, to 0, 1 or something. So now the key, like if you think about information theoretically, is actually very, very, very long. It's like exponential in the size of the in the size of the input. So like information theoretically, maybe you like actually can generate a random unitary even. But the point is that you cannot, like even though this key is information theoretically very long, you don't actually have access to it, you don't actually have access to all of it, at the same time. I'm giving it to you, again, as an oracle, so let's not confuse the oracle access to the unitary versus like this is the construction, like the construction of the pseudorandom unitary is allowed to have oracle access to a classical function. So this is known as the random oracle model, so I'm allowing you access to a random function. And so notice that sort of what I did here was I sort of relaxed the definition, but I didn't completely trivialize it. So now instead of saying that my key is short, my key can be very, very long, but I only have local access to it. So this is going to be this notion that we're actually going to show is very sort of interesting. And then we actually prove that it's a t-design. We show statistical security against t-queries, where t is some function that is greater than any polynomial. Sorry for this lambda here. It's greater than any polynomial. So again, if I was allowed to actually take this key to be like exponentially long and didn't have any restriction on how I access it, then I could have just sampled an actual random unitary, and I would also have exponential complexity, right? And I could have done this, but the challenge here is to do this with a very long key that you can only access locally. Good. So this is like yeah.
When you say locally, you mean that you can access f of a particular input, or what do you mean by locally?
I have oracle access to f. It's quantum oracle access, so I can access it I can access it in superposition as well. But
when you say local, you don't mean what is it?
I mean oracle access. Oracle access. That's
oracle.
Yeah. I'm trying to say the same thing in different wordings. Yeah. Yeah.
And what is lambda?
Yeah, I said that it's, let's think about lambda is equal to n here. So sorry, I should have replaced it. It just needs to be superpolynomial. When you ask me exponential and what, so sometimes you define a special parameter called a security parameter, lambda, and this doesn't have to be the same as the input size. But I didn't want to get into that like at this point. So sorry, this is like an artifact on the slide. Good, so let's say that we could construct this object, this sort of relaxation, this random oracle model of PRU. Now, how do I actually get a PRU? I want to be able to get a distribution with short keys. So now I just sort of go back and remember that I told you about classical pseudorandom functions. So what I'm going to do, I'm just going to replace this sort of actual random function f with a pseudorandom function. And recall that we said that a pseudorandom function has a short key, and if you're only if you're computationally bounded, then you cannot distinguish between a pseudorandom function and a completely random function. So whereas the original construction with the random function was statistically secure, once we replace the random function with a pseudorandom function, we get like a compact key, but our security is now only against polynomially bounded distinguishers. So this is like sort of a very common design step in cryptography. Like you all want to reduce your problem to an information theoretic problem. And then that's it. Yeah, you just get your PRU and you can go to the beach.
But are you going to explain a little bit about how do you prove statistical security, or where does it come from, the statistical security against, in this case, in the V to the F?
So the whole thing is, so this is like going to be, like this is like a goal for for people constructing pseudorandom unitaries. What I'm saying is that everybody who's constructing pseudorandom unitaries is actually trying to construct this notion that we call in the paper ROM PRU, and I am actually going to give an example of how people manage to do this. Okay, so we have this notion. So hopefully I convince you that at least it makes sense to consider this notion of ROM PRU, and there's like various perspectives that you can take. So you can think about it, if you're like a complexity theorist, we like to talk about reductions. So you can think about a ROM PRU as a reduction from like the functionality of a random quantum operator, from like a random unitary, to a random classical function. So ROM PRU just says, if you want to get something that looks like a random quantum operator, all you need to be able to do is to get like something that implements a random classical function. So we can think about it in this way. In the world of theoretical cryptography, we call this a black box construction of pseudorandom unitaries from pseudorandom functions. I assume for this audience this is less relevant. Anyway, so there's various sort of perspectives that you can take on this object of ROM PRU. And what I'm going to show next, as to Dorit's question, is how to actually sort of get this. So notice that like until fairly recently, like 2 years ago, people didn't know how to construct pseudorandom unitaries like at all. This was like a big open problem, and only like again starting 2 years ago, we started to have some constructions, and all the provable constructions are in this ROM PRU framework. And I'm going to describe this sort of maybe prominent this example that probably everybody gives, and this was the first one that was proven. It's called the PFC construction. And it's called PFC because it contains like 3 parts, P, F, and C. Yeah, it's like very insightful, yeah, of the authors. So what do? You have 3 parts to your function, to your unitary. So the first thing you do, you take your input and you apply a random Clifford on it. So if you recall random Clifford, you can actually generate like using a short key, like a polynomial size key. So that's not really a problem. Then I'm going to apply a random phase. So I'm going to take a random classical function, and I'm going to implement a function that takes x, the -1 to the f of x times x. So this is a binary, called a binary phase gate, random binary phase. And then the last step is apply a random permutation. So you sample a random permutation over the space of n-bit strings, over the set of standard basis elements, and you just implement this permutation. You implement this thing that goes from x to pi of x. And this is it. This is the construction. What MPSY and MH25 and like different, slightly different models show is that this PFC is a ROM PRU. And again, I told you ROM PRU is actually a T-design. It's like a type of a T-design that only takes local access to a random function as its key. So we can think about, like we were saying, it's a T-design. What is T? T here is equal to square root of D. So it's like exponential, but it's like still bounded. Yeah.
You know that all the components are essential in the PFC?
Great question.
Just a random permutation is also somehow random.
A random permutation is only so notice a random permutation is only going to work in the standard basis. If you're not doing things that sort of mix bases, then you're going to be in trouble.
Yeah, if I only take traces of like multiplication. Never mind.
So, but it's like a good question. People are actually trying to think about these things. Yeah. So it's like there are some answers and some I heard of some unpublished work that targets these things. So it's like it's an active area of research.
There's an upload from 2 days ago that drops the F.
Oh, okay. So it's online. Okay, good. Thanks. Yeah. So you can apparently you can show that just PC is sufficient. Good. So sorry.
But you know that P itself is not sufficient.
Yeah, so P itself is not sufficient. You cannot just do something in the standard basis, right? You're going to be it's going to be very easily distinguishable. For example, if I just take the plus state and I apply a random permutation, I'm going to get a plus state in the output, and a random unitary should not do this.
So
okay.
Zvika, this is
Yeah, okay, it's not going to be material for what we talk about today, but it is like a good point, so let me spend a little bit of time on it. So the question was, what if we just take a random permutation over the standard basis elements? Is this going to be enough to give me like a pseudo-random unitary, even heuristically? And I said, no, you can easily have a distinguisher. And what I was saying, let's just take a uniform superposition over all the possible x's. If I apply this permutation, I'm still just going to get a uniform superposition. Right? So what my distinguisher could do is generate a uniform superposition, send it over to the unitary, get the answer back, and check whether I got a plus state or not. And in like the P distribution, this is actually always going to succeed. I'm always going to get a plus state. Whereas if I actually like have a random unitary and I put in a plus state, like there's no way in hell that I'm going to get something that's close to a plus state. So the random Clifford actually sort of scrambles things in order for this to work. It's very interesting. There's very interesting sort of math that goes into this. It's a little bit orthogonal to what I was going to talk about today. Should organize a separate day on like pseudo-random states and unitaries.
I have another question connected to the pseudo-random. So Gil was asking, I think earlier, about just random circuits. So this is a different. So if you take the same depth, CP gives you some kind of it's a random permutation, so it's very hard to apply.
Getting random permutation is not going to be a random circuit.
But if you take a small depth, just random quantum circuits, do you know that it doesn't work?
We do, so I think there are conjectures for like some distributions that people conjecture that should work. The problem is that it's hard to prove these things based on like
What's wrong with random permutation?
What's wrong with random permutation for what? A random permutation? No, so you're asking about a random circuit? So I'm saying a random circuit is not going to implement a random permutation.
Why didn't you realize random permutation?
Oh, with a random circuit?
Yeah. This is a random permutation on the qubit, right?
No, no, no.
No, on the basis element. So just think about it as a classical, it's a classical permutation. It's a classical permutation.
So it's on the base
Elements,
so
yeah.
it's the number of qubits factorial.
That's right.
So why is it difficult to realize the problem is the depth?
So yeah, so first, good. Thanks for the. It's d factorial. That's right. Thanks, Miki. Not n factorial. It's d factorial, right? Because you have like it's a permutation on like how many basis elements do you have? The dimension of the Hilbert space.
On the basis element.
Yeah.
This would be difficult.
Right.
So this is not efficient.
It's not efficient, but you can do it with access to a classical random function.
But didn't you just say that the random permutation in the computational basis is not good enough?
Right. So that's why we need to do all this thing like CFP, like this. We need all of the components.
The last stage is random permutation in the computation.
Right. Yeah, that's true. So if I just had that, that would not be enough. You really need like this Clifford thing. Yeah.
Maybe I missed it, but is it efficient to generate random samples? Can we do this efficiently?
Yes. Yes. So this is like known. I'm not going to get into that. Yeah. So I will not go into how, but all of these things can be like implemented with access to a random function, and this random function like needs to have something like n-bit output, a little bit maybe more than n-bit output, and it's going to have just a 1-bit output, and this is actually enough to get all these things working. So this is great. Like you actually get a construction of a pseudorandom unitary, but let me be more greedy and say, okay, this is a great like solution, but maybe you want more. Like here, and this is sort of goes into the discussion, the little discussion that we had here. The security of the construction actually depends on the number of qubits, right? This t is actually square root d, and ideally we'd want to decouple these things. I want to be able to tell you what is like the power of my adversary, and you should be able to sort of construct like this function for me. I should not be able to, okay, let's be concrete. Let's say I want to get a 64-bit pseudorandom unitary, but I want it to be secure even against adversaries that run in time like 2 to the 256. This is like sort of standard cryptographic idea, right? You want, and I don't know, the way it looks like it's.
I'm just wondering. So you're using a random function, but everything here you can replace by a pseudorandom function.
Right.
Yeah?
So in the end, I'm going to replace it by a pseudorandom function. And by the way, for pseudorandom function, you can actually like get this notion of scalability. You can get a pseudorandom function that is secure even against an adversary that reads the entire truth table. So I said you need query X's and so forth, but like if you start from sufficiently strong assumptions, you can even get a pseudorandom function that is secure against someone who reads the whole thing. And maybe you want to get something similar here. So this is like sort of one motivation for doing this. This is like sort of taking it all the way. Like maybe even if I actually give you the unitary, like the unitary itself, you should not be able to tell whether it came from the uniform distribution, from the random distribution, or whether it came from like my distribution. And like this is something that you can hope for and is not achieved by this construction. So what we do in this work is sort of try to explain why this question of constructing a ROM PRU with larger t is actually sort of interesting, and why we should care, and sort of the some of the implications and directions in order to get there. I don't know what's like we're out of time or something. Should I just say our results? Well, okay, I'll keep going until the week stops. Okay, good. So
Yeah, you have time.
Stop me if you can. So what we do in this work, we make the ROM PRU framework more explicit. So as I said, all of the constructions that we know.
It's okay. You have 20 minutes.
Okay, good. I don't care. Okay, I'm gonna keep going. All of the constructions that we know actually use this framework, but we sort of made them explicit because we wanted to argue stuff about this object of ROM PRU. And so I told you that like in the literature, they know how to construct ROM PRU with t equals square root d. And what we're showing is that if you go a little further, if you can get it with t equals like d squared or something like this. So I want to argue that it's not such a big gap. Like square root d versus d squared, it's like a polynomially better ROM PRU, then you resolve this unitary synthesis problem, which hopefully I'll get to explain in the next 9 minutes, which is like, hopefully you agree is the fundamental problem once I tell you what it is, and sort of long-standing problem. So what I said before about this like scalable ROM PRU, like taking this, it's actually like a harder problem. So even just getting t equals d squared is like a hard enough, like is a worthy enough goal to aspire to. And along the way, we get like connections between unitary designs and like epsilon nets that Dorit mentioned, and I will mention as well. The other thing that we show is like a barrier. So why can we do it? Like how come like all the attempts that we had so far in the literature sort of fall short of either solving unitary synthesis or ROM PRU? So like turns out we need some new ideas.
Why is the construction that you already showed is not scalable?
Because you can only get t equals square root d. I want to get t. I want to be able to get t, to tell you what the t that I want, independent of d. I want to say I give you lambda and I want t to be equal to the lambda.
Why do you call it scalable? I mean, d is used.
Because you can because the security because security doesn't scale with the security sort of scale with the security parameter and not with the input size.
Okay, but it is efficient.
It's still efficient. Yeah. It still needs to be efficient. Yeah.
What about the key? The size of the key?
The size of the key should still be like short and bounded. So yeah, I should I get into like the actual like parameter setting? I think I won't. Hopefully it will not be too confusing.
It's order 1 or the square root?
No, it's never order 1. It's going to be polynomial in sort of the length of the input, of course, because I need to do things that like the number of qubits. I need to operate on this number of qubits, and also something like log t. Log of the amount, the design that I want to get. This is like the ideal thing that I aspire to. Like it can be it's so polynomial in log t and an n. This is what I want. And in particular, if I could do this, then I could get t equals d squared, no problem, because log t here is just 2 log n, so it's not. I should be able to get it without a problem. 2 times n, right? Not 2 log n. Okay, so we also have a barrier, and then we show that this like PFC construction doesn't even hit the barrier. So like maybe for maybe you can like even sort of getting to this barrier that we show, which is below like the thing that you hope for, might also be like a challenging task. But I'm not going to tell you all of this today. Hopefully, I'm just going to be able to tell you about this unitary synthesis problem. So again, as a headline, what we want is the question, so this was introduced by Aronson and Cooperberg, whether it's possible to reduce the hardness of any quantum computation to the hardness of a classical computation. So basically, let's assume that we have like a quantum computation that is very, very complex. It computes a very complex function. And what we want is to say, well, is it possible to divide it into like 2 orthogonal components? One is like a classical function that may be very, very hard to compute, but it's a classical function. And the other thing is an efficient quantum algorithm. So is it possible to take any quantum computation and separate it into an efficient quantum algorithm and an inefficient classical algorithm? So you want to decouple the quantumness from the computational hardness. Hopefully you agree, it's like a supernatural problem. And now let's be formal. We have quantifiers. So what we want to come up with is like a reduction. So what we want to get is like, so I said an efficient quantum algorithm. It's going to be an oracle algorithm. It's going to have oracle access to some classical function, and there's going to be just one of those. I want to construct this thing. I want to show you an algorithm, and this algorithm is quantum and efficient, and it has oracle access to a classical function. And what we want is that so that for every unitary operator, there exists a classical function such that if I feed this classical function into my reduction, I get something that is close to U. So efficient quantum algorithm, so like the quantum part is efficient, but it gets oracle access to a classical computation that can be arbitrarily complex. So like, look, this is existential. All I want is that for every unitary, there exists some function, and so that when we have like efficient access to this classical function, we can implement this unitary. So this is the unitary synthesis problem. Okay, hopefully you agree that this is like something that we'd want to know, like whether quantum hardness is like really quantum.
This is a question actually related to Shira's talk later, I think.
Okay.
It sort of asks whether quantumness is confined to a small circuit, or whether the more we evolve in the quantum world, the more quantumness we reveal, in some sense. The more quantumness we have to tackle.
We'll wait and see. Yeah. So I should say you can ask an analogous question about quantum states. So not about arbitrary unitaries, but about like quantum procedures that just output like a quantum state, that generate a quantum state. And this is actually known to be true. So we know that you can, like if you're only thinking about the hardness of generating a quantum state, then you can reduce it to the classical hardness, to the hardness of computing a classical function. And basically the classical function is going to be like something that depends on the classical description of your quantum state. So notice like a quantum state has like exponentially many coefficients, but we have a classical function that also has exponentially many sort of degrees of freedom. So we can definitely sort of encode, we can choose our like m to be large enough so that at least information theoretically, all of this information is encoded in the classical function. But the problem is to actually be able to access it efficiently quantumly in a way that will sort of generate the state or generate the unitary. This is like the problem. The problem, it's not an information problem. In terms of information, I can definitely encode any unitary inside the classical function, like the classical truth table, up to precision epsilon. But I want to be able to encode it in such a way that I can then sort of access this classical function, sort of what I called locally, and we objected to using this term, in Oracle access, and be able to compute this unitary on any input. Okay, and I should say that this, okay, so for states, people know how to do it. For unitaries, it's really not known. For some parameter regimes, it becomes trivial. Like, for example, if I said that R needs to be an efficient algorithm. If I allow it to be like an inefficient algorithm, then we can just use the information theoretic argument that I described before. I'm going to take an F that just encodes all the entries of U. And then R is just going to read the entire function F. It's going to query it on the first input, on the second input, and so forth. It's going to get the entire truth table. It's going to compose the unitary out of it and just apply it. So, like if you take the parameters to be large enough, then things become trivial. There is this recent work by Lombardi, Ma, and Wright that shows that maybe this is false. Like they show that if R is only allowed to make one query to this classical function. So this classical function can be arbitrarily complex and long and whatever, but you're only allowed one Oracle query, then you cannot get unitary synthesis. So maybe this is evidence. So there's like, you can discuss a lot about like the implications of this result. It's definitely very interesting. The best non-trivial positive result that exists is by Rosenthal. And he's showing a non-trivial construction. So here, like the R is not efficient. Its complexity is square root d, so it's like 2 to the n over 2. It's like exponential, but not trivially exponential. And yeah, you need a sufficiently big function. Like again, the function, the input to the function needs to be at least 2 log d in order to be able to encode the information in the unitary. So this is sort of the best that is known in terms of positive results. And yeah, so this is the unitary synthesis problem. And the next thing that I'm going to do is related to this notion of epsilon nets that Dorit mentioned. So basically, yeah. I don't know. I hope that you can do it, but it's hard. I don't know. And I think there's no consensus. Okay, good. So I want to relate it to this notion of epsilon nets that Dorit mentioned, and maybe we're going to stop like not much after that. So what is an epsilon net? It's like a set of unitaries that epsilon covers the entire unitary group. So for every unitary, there's an element in the set that is epsilon close to it. This is an epsilon net. Like if you think, or again, let me say it yet another way. So it's a set of unitaries such that if you put like an epsilon ball around each element in the set, like the union of the balls actually covers the entire unitary group.
What is close?
What is epsilon close? So you can think about operator norm. You can think about so all of the norms are actually going to be related by something like the dimension. So it doesn't matter that much which norm you pick here.
You don't want something which is dimension independent or control?
So I want many things. Yeah. So okay. Yeah. Or diamond distance is the thing that I have in mind at least. If you don't know what it is, it doesn't matter. There's some way to sort of define the distance. What you can see is, given this definition of unitary synthesis, you're actually implicitly defining an epsilon net. If you're just taking this, we have the reduction R, and we can instantiate it with the classical function f. And let's think about the set of all classical functions, right? All possible classical functions, like double exponentially many of those. You're going to get an epsilon net over the, if the unitary synthesis problem, if you have a solution to the unitary synthesis problem, it also defines an epsilon net over the unitary group just by sort of enumerating over all possible classical functions. So, and really it's not even just, it implies, it's really the same question, right? It's the question of whether you can come up with an R such that R sub f is an epsilon net is the same as the question of unitary synthesis. So we can think about efficiently generatable epsilon nets.
So you want the doubly exponential epsilon net? That's the question?
So
It has to be.
it has, yeah, so it has, right.
It has to be, but the question is whether this is fun.
The question is whether it's, so we know that it exists, the question is whether you can achieve it in this very special form, where you have an efficient algorithm that has access to a classical function. We don't know if the unitary synthesis problem is the question, does there exist an epsilon net that can be computed using an efficient quantum algorithm with oracle access to a classical function? And let's go back to recalling this notion of Rond-PRU that I described before, and I told you that we have these sort of unitaries that are instantiated by classical functions, such that if I take a random function, you get something that is close to the Haar random distribution or something. This is not exactly what I said, and I'll correct myself in a minute. So you can see that there's if this is, but at least this was my sort of aspiration, right? I want to get some distribution that behaves like Haar random, and we can see that there's a syntactic similarity between these two things. In some sense, what we have is that the unitary synthesis thing is a combinatorial version of the same problem, and Rond-PRU is the distributional version. So unitary synthesis says, can you reduce the hardness of arbitrary quantum computation to arbitrary classical computation? And Rond-PRU is asking whether you can reduce the hardness of a random quantum operator to a random classical operator. So it's a harder problem. Technically, this is not what all I was showing for the Rond-PRU is that they're approximate T designs. So this is I'm not saying that they're close to the Haar random distribution. I'm just saying that they're going to be a T design. So this gives us sort of what we're trying to, so in order to actually sort of formalize this connection and show that, so I want to show that there's actually a formal connection between Rond-PRUs and unitary synthesis. And this actually translates to showing a connection between T designs and epsilon nets. So let's try to parse this sort of conditional statement here. If I can show that I can start with an approximate T design and construct an epsilon net out of it, so if I have some reduction that takes a T design and gives me an epsilon net, then it follows that any Rond-PRU would solve the unitary synthesis problem. So let me explain why this is the case. So there's two things here.
This is the result? Or?
This is, no, we actually showed that this holds also.
Okay.
We actually showed that Rond-PRU implies unitary synthesis and some parameter issues. So if I can show, okay, so there's two things going on here. One is the syntactic aspect, where we see that Rond-PRUs and unitary synthesis have the same syntax. So in both of these cases, you get you have an efficient quantum reduction that has access to a classical function as oracle. And the question is, what is this thing implement? What is this reduction actually implementing? So in the case of Rond-PRU, it implements a T design, and in the case of unitary synthesis, we wanted to implement an epsilon net. So if we show that from any T design you can you can get an epsilon net, then this would imply that a ROM-PRU, which is basically a T-design with this syntax, is going to give you a unitary synthesis, which is an epsilon net with the same syntax. So this is sort of, we're actually showing that the connection between these two things is actually a connection between, like, you'd want to show a connection between these objects. Yeah, so I don't remember what is this slide. Yeah, okay, so I should probably wrap up. So let me just sort of gloss over the things that I didn't show you. So this question of the relation between T-designs and epsilon nets has been studied in the literature, but actually not in the metric that we care about. So this sort of goes back to the question about the metric. Yeah.
So the final result, do you go back to the final result that you actually showed, that the ROM-PRU means that if you have
a ROM-PRU, then you solve your
access to a function,
random
function oracle.
Yes.
Then you solve.
Yeah. If I have, so I said in the results slide, if I have a ROM-PRU with t equals d squared, so now like I need to show this connection holds, like what is the relation between t and epsilon here. So we need t to be equal like more than d squared in order for things to work out. So in this parameter regime, any ROM-PRU would imply unitary synthesis simply because a T-design implies an epsilon net. So sorry, this is not going to be. This is not today, maybe. So I want to say that like these things were studied in the literature, but not under the definition that we have. So remember, like we were talking about indistinguishability. And most of the work that I know about in the literature uses this tensor product expander framework, which I think is what Ole is going to talk about. I'm not sure, no. So yeah, so there was stuff that is known. We show other incomparable things because we use a different metric. Like it's much better, but it's under a different metric, which is incomparable, so it's incomparable. Yeah, we need to, and then we should like use it to show all the things that we need to show. That's okay. As you can see, like very puzzling things going on here. But let me just sort of wrap up. We want to be able to construct, like, so I hope this is like, at least I convince you that I am motivated to trying to figure out whether there exists ROM-PRUs that are better than what's currently known. And again, the best that is known in the literature is square root d. I guess you should look at this new paper to see whether they can do better. Can they?
Well, they don't do anything. Well, I don't know.
Okay, never mind. Yeah, okay. I don't want to put you on the spot. Right, yeah. This representations of the unitary group framework. Anyways, yeah, anything that's better than square root d, we don't know how to get. I didn't show you the barrier, like why this is like gets stuck. It's like a very silly barrier, but it's like we don't know how to there's no ideas in the literature except one of how to get around it, and like this idea that exists.
Say something about the silly barrier?
Yeah, so I said like that. Obviously, this function f needs to information theoretically encode all the information in the like up to epsilon, like an approximation of the unitary. Because if I give you like a T-design with sufficiently many queries, basically this is what we show. Like if t equals d squared, then you can basically, just by query access, you can actually learn the unitary pretty well. So like information theoretically, your classical function needs to encode the unitary. And this means that if I'm saying that the input size to this classical function needs to be long, it needs to be like 2 times n and not n. And like this seems very innocent. Okay, so now I'll go back to the slide with the question marks because like, and this seems very innocent, but it's like terrible because we want to implement a unitary that has n qubit input and n qubit output. And we know that we have to use a function we have to use a gate that has 2 n qubits. So we need to come up with a way to take our input and like expand it somehow so that we can like make a meaningful query. Like we need to actually be able to take advantage of all of the information in this function, right? Like it's not like, okay, it's a big function, but I'm only looking at a part of it. So I need to be able to expand like my input in order to get like a meaningful way to access this function. Fine, maybe. But like the hard part, I'm getting like an output, and this output really, again, it used this function f in like a meaningful way. So like things around this, like I get 2 n qubits that I don't know like what they look like, and then I need to be able to produce my n qubit output out of this. And like, how are you going to do it? You need to be able to get like this, you have a 2n qubit state, and you need to somehow coherently reduce it to like the correct n qubit state that that your unitary requires. And this is like, yeah. And like this brilliant, so there's this brilliant idea that actually manages to do it. And what they do is, what Rosenthal does is actually he uses Grover's search to actually, so you have a 2n qubit register and you just uncompute like an n qubit part out of it, and you can show, and like, I mean, you need to work, it's not like an immediate thing. And you can show that if you do things correctly, then you're going to get the unitary synthesis that you wanted, but you need to work like sort of exponentially, but not trivially exponentially. So yeah, so this is like the silly yet, and yeah, none of the constructions in the literature for like, and this is like, so this is for unitary synthesis. For ROM-PRU, we don't even know how to do this. So ROM-PRU with like, okay, there's too many parameters here, it's fine if you're like, this is not something that like sort of a general audience member here needs to follow. But yeah, so this is like something that we don't know how to do for ROM-PRUs, but even this idea for unitary synthesis. Okay, yeah, so we should do better. This is like basically the idea. So again, with unitary synthesis, we don't know if it's true. There's like this one query lower bound. Is it meaningful? Can you expand it? Can you get better results on ROM-PRU? Like ROM-PRU is like at least as hard as unitary synthesis. So maybe you can get better lower bounds. Maybe you can show that ROM-PRU is just impossible. So maybe we should stop thinking about it. Like save me some time. So like all these questions, many questions. Like the slide with all the relations between T designs and epsilon nets. This is like if you care about like quantum information theory, I think these are like, this is like there's a landscape of questions that that can be asked and answered, and like also like very interesting to understand what the right answer is. Yeah, it's like obviously I went over time, but thanks anyway. Just that it's possible, and you can even do it with one query. So this is actually it was already noticed by Aronson and it's on the Aronson Cooper paper. I'm not sure. So it was shown like when the problem was introduced, you could show that you can do it with like a polynomial time reduction. Basically, you have this. Grover, what do you call this thing where you can show that you can generate, if you have the PDF of a function, then you can generate a quantum state that corresponds to this function. Sorry?
The quantum state corresponding to the function.
Right, yeah. Yeah, if you have the cumulative, anyway, so there was a known algorithm that so basically if you want to be able to encode, so you take the description of the state. Thank you, thanks. So basically, it was basically known, but you needed to observe that this actually helps you to solve this thing. So you take your quantum state, you think about it as an exponentially long vector, and you encode like you think about it as you think about the induced probability distribution, and you encode like the PDF of this the CDF, sorry, not the PDF, the CDF of this function in a classical oracle, and then you just apply like sort of known algorithms. More recently, it was shown that you can actually do and this requires a polynomial number of queries. Basically, for each qubit, you do like a rotation. For those of you who know this algorithm, you know. Yeah, more recently, you can show that you can just do it with one query. So this is like super interesting that you can actually do it. Yeah, so this is what's known.
But there's any idea that
how do you do it with one query? So I don't know it that well, but okay. So here's the I think. So what? Maybe we'll do it. Yeah. Yeah. Sure. We can ask ChatGPT. I'm sure it's gonna.
I have a question.
Yeah.
In the PFC construction, does the sequence matter?
Yes. Yes. So F and P are actually sort of actually compute. So the order of P and F doesn't matter. It can be FPC, but you need to do Clifford first.
Insight into what all of these do to the Hilbert space? Here's what I can imagine.
Yes. It's in the papers, but yeah. But I can say more about it, but I think it's just probably not the best setting.
Okay, let's have a coffee break.
Let's reconvene 5 minutes after, like. כן, אז אבל עכשיו